Good. Well, then let's start. Thank you very much for joining in and welcome. It's my great pleasure to actually talk in front of you, and it's also very new for me because I'm not a bioinformatician or a biologist, but I have crossed paths with them in several occasions, and this new stuff that I'm presenting here seems to just be another instance of that. So I'm really happy to hear your feedback or opinion on what I'm going to show you. So let's start. Okay, so about me, I mean, I was already introduced right now, and with really a lot of passion, I am heading technically an effort called Brainome, which is basically what I'm going to show you today. I'm also with passion teaching at UC Berkeley, mostly data science. And originally, I started working in machine learning in 2001 because basically as an undergraduate working on neural networks. And in 2001, nobody cared, right? Now everything seems to be AI and machine learning. And in 2001, neural networks were sort of esoteric. And it's interesting because I often, it makes me very old or feel very old, but what's now a product used to be a homework. So it's kind of interesting what happened here. So I want to start with a very simple game, okay? Before we go into any depth, let's start with something really, really simple. So if I gave you the sequence 2, 4, 6, 8, and I think almost automatically you'll say 10, right? And almost automatically you say 12. And of course, that's true. That's what I'm aiming for here, right? 2, 4, 6, 8, 10. And the interesting part here is, why do you do so? Well, because, you know, we've somehow trained ourselves to actually, and we'll see that it's not just training, it's actually innate. We basically trained ourselves to immediately look for the rule in some data, right? So this is +2, right? Or all even numbers, right? And so once you have that, it's really cool because once you have that rule, I could give you the number 100,000, and you would say, well, 100,002. That's one interesting thing here. So you can actually use the rule and apply it to unseen data. So in machine learning, we would call that we can generalize. Okay, so now the validation set that you use in machine learning, you know, would give you 100% accuracy because whatever number I put in there, you can tell me the next number. Now, the next question is, if I gave you just 2, 4 though, how would that feel, right? It would not feel complete. It would feel like there's not enough data. If I gave you 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, at some point you would tell me to stop, right? Because what do you do with that? I mean, you already know it's +2. Why are you just bombarding me with more data? And right here, we see that there's something interesting happening, because wasn't there Google's rule that there's no data like more data? Isn't there more data like more data? Well, it turns out there's not no data like more data. We'll figure out in a sec what actually should be the rule. Because we can look at the second sequence. The second sequence is 6, 5, 1, 4. So what's the next number? And, you know, it's a trick question. I intentionally chose those to be the last 4 digits of my phone number. Now, our phone numbers are, unless you pay for them and get a 1-800 number, they're completely random. So the idea is you can't just figure out somebody's name and map it to a phone number. No, it's a completely random number. And the interesting part of that is, what can we do with that number 6514? What can you do with a phone number? Well, there's no rule to it. You can only memorize the number itself. And so the problem here is, if you only memorize the number itself, you can actually not answer the question, what's the next number in the sequence? So in this case, you would say, maybe with more data, maybe, but maybe not, right? So the trick here is that it's not about there's no data like more data. It's about there's no data like enough data to extract a rule. And so the talk here will be, and I'll give you the overview of the talk in the sequence, will be all about that. How do we know that we can extract something from our data? How can we measure that? and I see there's a question. So next number is not minus, you know, you could infer that the next number is -3. I've seen that before, but the point is it's actually a random number. So there is no answer to the next one. And of course, by inferring -3 out of a random number, you're doing something that humans like to do a lot. That means overgeneralizing. We see overgeneralization as a political problem, right? All black people are criminals. It's an overgeneralization, and it's of course wrong, right? But because it's an overgeneralization, it's very easy to get into that, right? Or all women are this, or all men are that. These are all overgeneralizations. So that's another problem. So just to jump ahead on this, so we need to find out, and that's the major point, is the trade-off between accuracy and generalization, right? And that's basically what we're going for and what we always have to go for. And we would have to, obviously, now we use a validation set on 6514, we would figure out that -3 could not be the rule, right? I mean, but that's a different story. It's just an academic example. Okay, by the way, thank you for asking me a question, because I want to have this maximally interactive. If you feel I'm going too fast, or if you have, you know, an interjection like you just had, which I'm really grateful for, please go ahead and do so. Okay, so because I am, you know, there's going to be deep stuff in there, and there's going to be, you will have questions, and don't bottle them up, bring them out. I have intentionally less slides than I usually have, so we can be more interactive. So what is this talk about? This talk is about 3 things: the theoretical underpinnings of measurements in machine learning, the measurements that I developed together in this company, Brainome, with a lot of smart people that are actually derived originally out of physics and information theory. And the next thing is I show you 2 practical applications where these measurements are extremely useful, so I find. And then also, I try to give you a perspective of why you should care and how you can actually use these measurements to make your product and your machine learning and your data science more systematic, and therefore hopefully faster and better and more understandable. And we have to start very top. We have to go to the very foundation of what we're doing. And the very foundation of what we're doing in the sciences, in biology, chemistry, physics, is that really we look at phenomena in the universe, right? And of course, biology restricts itself to living beings, and then chemistry restricts itself to the interaction of particles, and physics tries to be more general. But the interesting part is that in prediction, so what we do is we observe something like an apple falling from a tree, right? So the apple falls from a tree, hits Newton's head, and Newton says, ouch, okay? That's the first thing that happened according to the legend. And now the question for Newton was, first of all, why does it hurt? I mean, why does the apple even fall from the tree? So he asked the why question. And the next question was, why on earth, how on earth does the apple fall from the tree? So if I put the apple higher, is it faster? If I put it lower, is it slower? Also, does it depend on the size of the apple, right? And of course, we know that the answer in the end was a formula E equals mgh to basically get the potential kinetic, get the potential gravitational, get the kinetic energy out of the potential of the gravitation. So now the question now is, before we even go to the whole chain of science and physics, the first cycle here in this graph, where we basically say we have experiments that create observations, and then are then basically fed into a theory. So then the theory will predict the experiments. And we are very, very happy the moment our theory completely predicts the experiments, right? The moment we have something that says, I don't have to do experiments anymore. I don't have to drop any more apple because I know it's E equals mgh. Then you don't have to drop any apples anymore, because you can mathematically find out what the next apple drop will actually measure, right? Plus minus some noise. And that's as old as Socrates. I mean, this scientific method has been documented a long time ago. And I usually come up with all these Western examples, which is just my culture. But the point is that in China and in also in the Arab world, there have been independent efforts to do the exact same thing. So this seems to be innate to human, at least to humans in some way. The scientific process is really old. So now why I'm talking to you about something old, right? Wouldn't you rather hear about something new? Well, there's two new things, and these are the two boxes downstairs below that are actually quite new. So the first thing that happens once we had computers, once we introduced computers, is that you could have a theory, right? And say, well, we don't really know, we can't drop so many apples, maybe they go bad, but reality is most likely we can't drop so many nukes because nukes are dangerous and have a lot of impact of the environment. So we need to simulate, right? So what happens is theories were created based on a couple observations. And then we take the theory and simulate and see if that still seems intuitive, okay? It's still obviously kind of, hand wavy because we don't know really if that's gonna happen, but at least, we were thinking if physicists or a biologist or chemist with a lot of experience could go look at the simulation and then say, ha, this is what I've seen, this makes sense. That was in the 1950s when we introduced computing. But now something else happened, and that is basically the really modern thing. That's the 2000s, basically, where we went and said, you know what? Let's not put the theory in and see if the observations that come out make sense. No, let's just put the observations in and then see if the predictions make sense. And that's called machine learning, right? And there's of course something interesting there, because if you take the machine learning green box and put it onto, if you just basically flip the image by 90 degrees, you would say, yeah, wait a minute, so machine learning is replacing the theory? And that's the problem, right? Yes and no. The answer is, yeah. What if you had a perfect machine learner with 1 million parameters? Awesome. So now you have a perfect predictor, but you haven't understood anything. You have to ask the computer. And how does it fit into the scientific framework, right? And the next question is it really perfect? Are all these predictions right? How long are they valid? What do I know about them? It's a really eerie feeling of, wait a minute, did I just get my brain replaced into a computer and I have to ask that thing? That was not the idea of science. The idea of science was to promote progress, by human understanding. So the question here, that creates a problem. But that's number one. Number two is, wait a minute. So if basically machine learning is theory building, we should be able to apply the same principles that we know over hundreds of years by understanding the scientific method to theory building, to machine learning as well. Because the trick is that we know things like Occam's razor, and I will talk about this in a bit. We know that the shortest explanation that fits, the observations, that means short means generalization, and actually fits means accuracy, is usually the best, or at least we believe in that because over many years of experience, we have found that out. So what I do and what I understand as data science is to try to apply these principles that we have from the ancient times pretty much of the scientific process and how to build theory to machine learning, and ask myself, how would the machine actually be the best theory creator in some way, okay? And for me, that, by the way, is what I call data science, the science of automating the scientific method. And let's go maybe a little deeper into that. So let's talk about the scientific method, right? The scientific method pretty much always works like this. You have somebody measuring, performing experiments. Now, what's the next step when you perform experiments? The next step is you put your input and the resulting experimental result into a table. You have to basically notify, you have to write it all down. And the more experiments you make, the more you hope that you can come up with something. Now you do all of these experiments varying the various factors that you need to do. And then later on, you hope that you can actually look at those experiments and be smart about it and somehow predict what the rule is, right? For example, you go and plot the table in various ways based on various factors, measuring correlation, all of these statistical methods, right? We all know, and also non-statistical methods, right? So that's basically the scientific process in a nutshell. And what we hope is that we come up with something really smart, maybe like Einstein's E equals mc squared. Now, if we do the new scientific process, the data science scientific process, then actually nothing changes. The only thing that changes is that instead of that brain that tries to figure out what the hell is the rule, we have computational logic trying to figure out what is the rule. And so now, obviously, it becomes a computer science problem in the sense of, how do I change that computational logic such that it comes up, hopefully in the end, if it can, with something smart as like E equals mc squared, with something really understandable and precise and good. So that's the trick. And in order to get there, we are in science, right? So we need to work with definitions and we need to work with concise language. So I want to give you some of the thought framework that I teach in my class at Berkeley on how to get there. So the first thing is, what actually is intelligence, right? So we talk about artificial intelligence all the time, but what the heck is intelligence? So now, this definition here is not complete. And in fact, part of the work that I'm doing in the discussion group every 2 weeks is to actually come up with a better definition. But for now, we can work with this definition, which is intelligence is the ability to adapt. And that is the definition by Binet and Simon from 1904. And of course, it's very human-centric. It's saying the ability of humans to adapt, and that actually has some context, that has some connotation to it. And Binet and Simon, by the way, are the inventors of the IQ test. And if you were to take a current IQ test, you would take the Stanford Binet test, which actually is named and also derived from the original one from 1904. Now, how do we actually use that for machine learning? How do we actually transfer that over to machine learning? Well, what does machine learning really do? What do you do if you train a neural network or a decision tree or something? Well, we actually adapt a finite state machine to an unknown function based on the observations, okay? So the adaptation happens by adapting sort of the computer rules, whatever they are, based on a decision tree or based on a neural network or based on a support vector machines. These rules, they have parameters, and these parameters are adapted such that it fits an unknown function based on observations. Now, I will talk about unknown in a bit because it's not really unknown. We need to make sure what unknown here means, but basically we have observations and we want to model the table that we are given, right? And of course, we want to model the table. So basically we have n rows of observations, which we usually call instances in machine learning. In machine learning, each row of the table is an instance. And it has a header, right? So your header will usually be, maybe size of an object, weight of an object, appearance, gender, or it could just be genomics, right? It could just be 21,000 genes, right? That's your header, and then there's a target function, okay? So f of x is a function, basically, of that vector of all your columns that will say, well, we cancer or not cancer, based on the RNA sequence of a cell, something like that, right? So we will from now on in this talk and kind of forever in the theory of this, assume that our input is a table like this. So we will assume it's supervised machine learning and we solve a classification problem. It could be binary or multi-class. And for the brevity of this talk, I need to actually not just look at just binary, but I can also need to go to balanced. So for everything we do right here, right now, because of, I only have limited time, our f of x will be zeros and ones only, and balanced. That means the same amount of zeros and the same amount of ones, okay? And so our output of the machine learning problem is actually a finite state machine, okay? It could be a neural network, it could be a decision tree, it could be a support vector machine. And people are often surprised that I call a neural network a finite state machine, but it doesn't matter what it is in your head. In the end, it runs on a finite state machine, right? It runs on your laptop, which is nothing but a finite state machine. We don't have Turing machines because Turing machines have an endless band. So in reality is we have a finite state machine with finite memory and a finite number of possible states. So what is the finite number of possible states? Well, for n bits of memory, it's 2 to the power of n. Now 2 to the power of n is a huge number, like for a laptop with 4 gigs of memory, right? That's more states you can ever count before the universe ends, but it's still finite, okay? So, and that's why what we do, whatever we do, we take that table and model around with various algorithms that we know from the machine learning community, a finite state machine that hopefully implements that function that is in the table. And now my question is, when is that actually a better thing than just keeping the table? What about the table anyway, right? So it's actually, we don't actually have a real unknown function. We actually know the function, or we know a sample, we know samples of that function. We know that when we did an experiment, there was this input and it mapped to that output. There was this input and it mapped to that output. And we call that a table, right? That actually is a model of our function. It's there. And it turns out that if you were to repeat the exact same experiment again, you would already know the output. It would be exactly in your table. All you have to do is look it up. That's why we call it a lookup table. So now the trick here is you have a lookup table that has n rows, right? And that means it has n lookups, okay? So if you had a big enough table, chances are that the exact same lookup can happen again. And guess what? Then you'll find. But what we really want is something else. What we really want is that you don't have to use a lookup table, but that the values in between, the experiments that you didn't do, can also be predicted. So what we want is we want generalization, right? And so, as I said before, we want that we stop dropping apples for real, and we actually find out predict what, how the apples will fall. And that's exactly generalization. That would be filling in rows and results of the table that we don't have. And now the question is, how would we model this in a finite state machine so that we can actually do that? And then we also know from statistics a very well-known problem called overfitting. So we do know that when we overfit, we don't do that. When we overfit, we basically took the very simple lookup table that we know and created it into something really complicated that has no value for generalization. It just also looks up. It's just more complicated. So we already know we don't want something more complicated than the table that just gives us the same value. So we want something less complicated, or maybe even more complicated than a table, but that is actually able to predict. And now here's the interesting part. Let's think about this in a little more physical way. So what does each row of the table actually represent? Each row of the table represents a state transition, okay? We go from this input to that output, from this input to that output. That's an arrow, okay? That arrow, by the way, also appears in the transistor symbol. If you ever know, that arrow is a very powerful arrow. So we will denote this arrow as a state transition. And by the way, if you ever took computer science, you will know that if you draw a finite state machine, you draw all these arrows. These are just the state transitions, okay? So the question here is, for a table of n rows, I need n arrows, obviously. And with n arrows, all I can do is look up. Now, what I want to do is I want something that is better than lookup, and ideally actually uses less than n arrows, because remember before, really the goal was to get E equals MC squared out and not just, something complex I don't understand. So what it means here is that we want something that creates a rule that's very simple, like +2. And now we can actually know, all the arrows would be represented by from 2 to 4, from 4 to 6, and so on. No. We only have one arrow, which is give me this and I give you the rule on how to do addition +2. That's what we want. So what we need to ask ourselves is, if we want something simpler out, which is also, by the way, Occam's razor, then the big question is, how many state transitions does the finite state machine, which I denote with M, need to model the training data? That is the big question, right? So you have some training data, and if you use neural networks, how many state transitions would it use? How many parameters? Or how many state transitions would be used in the decision tree? And of course, state transition in the decision tree is, again, each branch, right? And so that is the theory framework. I would say this. We have something called intellectual capacity of a machine learner. The intellectual capacity is the number of unique target functions a machine learner is able to represent, okay? As a function usually of the number of model parameters, but doesn't have to be. So the number of unique target functions a machine learner is able to represent. The way to visualize this in your head is to think of a table that you have, and then you label it 0, 1, 0, 1, 0, 1, 0, 1. And the question is, can all 0, 1 labelings that you dream up in your target function be implemented by the machine learner or not? And in order to answer this question, I will normalize it to the lookup table. I will say a machine learner's intellectual capacity is memory equivalent to n bits when the machine learner is able to represent all 2 to the power of n binary labeling functions of n uniformly random points. So you take your random points, and I say, okay, here's what. With that neural network, if your table is 10 rows, that neural network, whatever labeling you can come up with, can do it. And that will give it the memory equivalent capacity of 10 bits. Okay, 10 rows. Why 10 bits? Because in binary balanced case, you would have each experimental outcome be 1 bit of value, because 50-50%, 50-50 chance gives you 1 bit. So that means that an experimental table of 10 experiments where you have a balanced binary output can only have 10 bits of total information that come out of the table. If it wasn't balanced, then it would be less than that of information. But the interesting part is, I can now say my neural network, my decision tree, my support vector machine is memory equivalent, has a memory equivalent capacity of 10 bits. That means any lookup table of 10 bits can be memorized by this, algorithm, basically, by this neural network, by this support vector machine. And the most important thing here is that we're still just memorizing. And that's a problem, because when the MEC at memory equivalent capacity or higher, we're able to memorize all of them. But we don't want that, because that would just be converting the table into something more complicated. We want something where we actually say, the representation that I have is now much smaller, because now that allows for prediction. And I'm going to show you that on this slide. So the main trick, and the main trick of Brainome, is to basically say, we don't want to memorize. Yeah, sure. Your +2 rule could be expressed as +0.1, +0.1, +0.1 until it sums up to +2. And then it would obviously be longer than 2, 4, 6, 8, 10 that I give in. But the trick is, what we want to do is we say, no, we make this engineering assumption that we want your machine learner to basically be a compressor. We want you to use less parameters than you would need for memorization, okay? And so we will say memorization is worst case generalization. That is the trick. So 6514, yeah, you can memorize, but you can't generalize because you don't know where it goes to, right? Or you could generalize, and it's probably overgeneralization. So for us, for right now, memorization is worst case generalization. If we deduce nothing from the data, the only thing we can do, just as in the 6514 example, is to memorize the observations verbatim. Then we're not better than the table, because that's what the table actually does. It memorizes the observations verbatim. And using as many parameters as needed for memorization is an indicator that the machine learner did not actually deduce anything. We're overfitting. No rule could be extracted. When a rule is extracted, we assume it needs to be smaller than the original. And that assumption is Occam's razor. That's basically saying it needs to fit and it needs to be small. And Reducing, that means reducing parameters below memorization capacity will, in the best case, make the machine learner forget what's not relevant with regards to the target function. So that's also interesting. If you learned the rule plus 2, 2, 4, 6, 8, 10, doesn't matter how you learned it. The point is you know the rule plus 2, so you know how to apply it. And if you ask yourself, in the things you learned in your life, do you remember how you learned them? Most often you completely forgot how you learned something. You just know you did. You just use it, you use it, right? So what it is our brain does the same thing. It tries to not memorize, it tries to extract rules all the time. This is also why we fall into traps like overgeneralization, right? So now, given that, we can actually create a mathematical definition of generalization. What we will say is for balanced binary classifiers, that the number of correctly classified instances in bits, right, divided by the memory equivalent capacity is our generalization. So again, this is binary balanced classifiers, and the binary balanced classifier, each row is 1 bit of information, right? So that means each correctly classified row is a bit of information. And if I can make that happen in less than the memorization capacity, so basically I can have some compression, then my generalization here, my G, will be greater than 1, which is great because I'm on the track to generalize. But if my G is smaller than 1, that means actually I needed a lot more memory equivalent capacity, a lot more state transitions internally in my finite state machine than I would have needed in the lookup table. Well, then most likely I probably just have a more complicated lookup table, right? Yes, it could still generalize, but the point is, and trust me, the empirical results is that yes, there are exceptions where it still generalizes, but the reality is, it's, as an engineer, we want to build a car with 4 wheels, and 5 wheels works, but it's actually much better to build a car with 4 wheels. And that's what we do. We say, when we need to be as far below as memory capacity as we can. We need to be way more general than the lookup table. And so there is a caveat here, which I'm not going into because it's a lot of details. There is, of course, something like a Shannon entropy. And there's, of course, something like the law of large numbers. When you have a lot of attributes, it turns out that there is another boundary, which is not G equals 1, right? So obviously, it's for small data sets, it's clear if you have a number of correctly classified instances divided by memory equivalent capacity is 1, then you were just memorizing. But it turns out you can actually put random numbers into machine learners sometimes. And even though it's not generalizing, you get like a 2-to-1 or 3-to-1 generalization thing. So that goes into what's called the information capacity of a machine learner, and you can measure and also analytically analyze that. It's just using information theory, and you'll find out there's another limit which we call GMEM. And basically, once you're above GMEM, you can be sure you did not overfit the data, okay? But in general, for small problems and for easier way of accessing this, you can say, well, once G is greater than 1, that's good news because I already simplified over the lookup table. There's also something very interesting about this formula. In general, when we don't calculate this formula, we don't measure generalization, we have this problem that we really can only post hoc, test against the validation set. And the problem here is that then you have IID requirements. You want it to be identical but independently distributed. And this is super hard to guarantee. This is a standard problem all the time. Like, how do you guarantee that? Here, for this definition, the only requirement is that the points are distinct, right? Obviously, you shouldn't count the exact point again, because that just screws you up. There's no distributional assumption in this measure. It's not like we need to have a Gaussian or we need to be, binomial or something. No, this is just a measure. And it doesn't contradict any of the current methods. So it's just an addition. You can now obviously do the same with training, validation, and benchmark sets, right? So you can actually measure If you just trained on training, what's the generalization? And then if you validate, you can now say, okay, and that generalizes to the validation in this way, the number drops like that. And if you have a benchmark set where you test it completely blind and then, but you know the answers, you can even that. And you can see the generalization drop along data sets, for example. There's a bunch of things you can do with that measure that really help you sort of understand these, and because a couple of these assumptions can be dropped. Now, the bigger question is, how do you actually calculate the memory equivalent capacity of these different machine learners? How do we get to that number? Well, this could be binary decision tree. That will be the depth of the tree. That's really easy. So if you have a perfect binary tree, each tree is another bit of information. Each layer of the tree implements another bit of information. That just gives you an idea. So for a decision tree, it's trivial, and that's pretty much solved by Shannon. If you want to know more about this, by the way, I encourage you to look up something called the Shannon number. The Shannon number is the difficulty of implementing a chess game and how complex the chess game is. It turns out the memory equivalent capacity of a chess game is 400 bits. Now, for a neural network, we don't know. For a neural network, it's Brainom's work. I don't have enough time to present this here because I also want to go to the benefits for you. But then there's a bunch of things we don't know. Random forest is still to be determined. For support vector machines, still to be determined. KNN, GMMs, all of these have a number of parameters that memorize, but we need to figure that out. By the way, if you want a better intuition for how this works, take a look at this. I have this visualization. It's a TensorFlow visualization. So TF meter is basically TF meter is what we call TensorFlow meter. And the TensorFlow meter is basically an implementation of the TensorFlow playground that probably some of you know, but with added measurements. So you can totally like build your own neural network, see the capacity, and then compare it to capacity requirement that we have on the left and try to train it and see how these numbers all fit, okay? So that's something to just play around with as a fun toy. Now, again, what I gave you now was a very, very, very quick overview of machine learning as an engineering discipline, okay? So we were basically saying supervised machine learners have a memory equivalent capacity in bits that is computable and, by the way, also empirically measurable. And in this kind of, usually I present a lot more, but I have to be quick here. We know that artificial neural networks with gating functions have a capacity upper limit that can be determined analytically using 4 principles. There's a paper that is linked on our website and the documentation that will show you how to actually do that. And also, again, there's the app. And effective capacity can be measured on actual implementations. So we actually did measure the capacity for different TensorFlow architectures. We did measure the capacity for scikit-learn, which, by the way, behaves the best. And we also measured the architecture for Keras for different versions. And yeah, that's sort of the other end. Anyway, so predicting and measuring capacity allows for obviously all kinds of things. For example, you can now say, well, TensorFlow is better than Keras, but it's not as good as scikit-learn or something, right? And that allows you to actually do engineering based on your machine learner. Now, you don't have to do all of this. The funny thing is, we do that in Brainome. So Brainome does all this engineering work that you need to do, that you could do for you. It's like, we do this for you. And one thing I want to say, if you say, well, I'm totally happy with my neural network, then consider this. In fact, you probably trained it for a long time. There's a lot of energy, and it's bad for the environment after all. But it turns out you will see that in general, the less parameters you use, the better is the generalization rule. The higher the adaptation per parameter, which is the higher the chance that an unseen instance can be predicted correctly. And you will need less training time to get there. And you will also need a lot less memory, and you will be able to do a lot more with it. And again, there's another paper on this, which is less parameters give a higher chance for expandability. It's basically just Occam's razor. And I invite you to take a look at this too. And again, for people who are not so familiar with Occam's razor, I want to show you Occam's razor from Wikipedia, which is kind of a funny one. Among competing hypotheses, the one with the fewest assumptions should be selected, right? And of course, in our case, the hypothesis would be, how do I generalize the table to values the table hasn't seen, right? So that makes total sense. Now, Wikipedia wasn't sure that among competing hypotheses, the one with the fewest assumptions should be selected is the best description for Occam's razor. So they had a second attempt to it. The second attempt was, for each accepted explanation of a phenomenon, there may be an extremely large, perhaps even incomprehensible number of possible and more complex alternatives, because one can always burden failing explanations with ad hoc hypotheses to prevent them from being falsified. Therefore, simpler theories are preferable to more complex ones because they're more testable. Well, that explanation is true. I prefer the first one because of Occam's razor. Right? So funny enough, look this up on Wikipedia. They pulled a meta joke on themselves. Okay. So sometimes you need more information, but reality is among competing hypotheses, the fewest assumptions, the shortest explanation length, right? And you could say, wait, why this is an assumption? Well, the assumption is that the parameters you chose for your neural network are actually the ones you need to do to generalize your table. That's your assumption. So you want the fewest parameters, right? So now, what you just saw is the introductory conceptual framework that I teach over an entire semester at UC Berkeley to CS grad students. But I don't want to bore you with this. I want to show you how this stuff actually works in the sense of what it does and what it helps us doing, and then also how you can use it. Before I jump there, are there any burning questions? Okay, so I'm just gonna go through it. So first one is, we at Brainome, we have a machine learning solution that needs zero hyperparameter tuning. Why is that? Well, because we don't tune, we measure, okay? We will measure everything. We measure it based on information. And we test our approach against 176 OpenML datasets. OpenML is sort of a democratizing machine learning database with various tasks. They range from financial, biomedical, speech, vision, all of these problems. And we just took a data set that was meant to test AutoML approaches. And we decided, okay, let's do it. So we run through 176 OpenML tasks within 2 days, by the way, or basically 1 day on 2 computers. And for all the 176 data sets, our measurements result in a model that is about 2 to 3 orders of magnitude smaller than what they report as state-of-the-art on the site. And it requires about 100 times, 1,000 times, or again, 2 to 3 orders of magnitude less training time. It's so much faster. Now you'd say, okay, maybe it's fast, but is it good? Well, 85% of the tasks are solved above state-of-the-art accuracy. So we have models that don't need to be tuned. You could just say, oh, do it, bum. In fact, our tool literally takes the URL from OpenML, does all the pre-processing, creates the model with measurement, and outputs a predictor. And by the way, all these predictors, you can look up online. github.com/brainome/OpenML. You can reproduce these results. I don't want you to believe me. I want you to look at the reproduction of the results, okay? Don't believe me, check it, okay? And it tells you for each predictor how long it took. It tells you for each predictor what the validation accuracy was. It runs the predictor on that data. You can basically literally reproduce our entire experiment there. And again, in 85%, we're more accurate than state-of-the-art, but it's not a completely fair comparison because a lot of the accuracies there are reported without obviously measuring generalization. That means we don't know if they're overfitting, right? Sometimes they're just overfitting because and then also, to be frank, some of the data sets are so malformed that there's probably no other solution than overfitting. And of course, we work very hard not to overfit. We have a parameter in our tool. If you say risk overfit, then we'll actually behave like currently state-of-the-art behavior is. But we then also generate a lot of parameters, and then we get to all the old problems. So we prefer to basically find the best trade-off as of measurement between generalization and accuracy and report those numbers. So what is interesting for you is this is a low entry barrier tool. You just run it on your data set and see what the output is. Done, right? Boom. And you don't have to know anything about machine learning, to be frank. I mean, you just run it. You don't need to install a TensorFlow or PyTorch or something. You just run it. That's it. Value proposition number 2, it gives us, all of this obviously gives us a way more scientific / systematic approach to machine learning. Now, if we take a look here, we'll see, for example, what we did is we took a Nature article on an immunology case study. It was viral versus bacterial versus non-infection based on RNA sequencing. And we wanted to see, okay, that's an interesting article because it talked about the fact that they were actually able to generalize from an RNA sequence to whether there would be a viral, bacterial, or non-infection, right? And I mean, it's a Nature article, okay, after all. So we went in and said, well, let's take a look at the article and how we would do it. So, and this is the table of results. So they got their article published with 109 instances of data, which is actually 109 patients. So that's something. And their number of attributes that they selected out was 29. They had 3 classes: viral, bacterial, no infection. And then their class balance was actually not so very balanced. So, and it obviously right there gives you a best guess accuracy of just guessing the majority class gives you 64.22%, right? Now this was all reported. But then we have other measures, like for example, if you take a look at this data, can we actually learn it? And so how do we do this? Remember the 2, 4, 6, 8, 10 from the beginning? Well, I said to you, if you have 2, 4, then it could be 6, but it could also be 8 or maybe 16, depending on the rule you can come up with. And so that's what we do. What we do is we take 10%, 20%, 40%, and so on of the data and ask ourselves, the perfect machine learner, that obviously doesn't exist, but sort of in a Shannon entropy sense, perfect machine learner, would the perfect machine learner actually be able to model this data? And what we want is that this number converges. So basically what you see here is actually convergence. So 10% needs sort of 4 decisions, 20% needs 5 decisions, 40% needs 6 decisions. And guess what? 50, 80, 100% of the training data actually stay constant at 7 decisions. So there is a high probability that there's actually an extractable rule, because as we add more data, we have enough data. It's like 2, 4, 6, 8 was enough data. So now we add 10, 12, 14, 16. The rule doesn't change. We're still at 7 decision points. So we can keep that. So that is good news for them, but they didn't know that, right? Now the estimated memory equivalent capacity for a decision tree for us before we do training was 52 parameters, and for a neural network was 201 parameters. They don't even in the article say after the fact, once they train all the models, how many parameters they use. How many parameters they use is not part of their equation of this article. And then we actually can calculate based on the amount of parameters. We can calculate the memory equivalent capacity, and based on the memory equivalent capacity, and obviously then knowing the class balance, we can go and get the expected generalization, which is 2.06 bits per bit in a decision tree, and in a neural network, 0.54 bits per bit, which is a problem. So we already know a decision tree is better for this particular problem. And now we do processing time. So they in the Nature article don't even talk about processing time. I think processing time is not something that's currently measured by people. Just for your information, we take 5.22 seconds. So to build a decision tree of that data is kind of trivial. And they use the neural network. Why? Because it's probably the hype, right? Deep learning is the big thing. Well, we use a decision tree. And they can't even compare the accuracy because they wanted to enforce sort of ROC curves and so on. So they only do pairwise comparison of the accuracy. Well, we do a whole 3-way classifier, bacterial, viral, non-infection, and we get to an accuracy of 100%. So once you have an accuracy of 100% and you know you're generalizing, which we know because our generalization ratio is 2.09, we know we've solved the problem as much as we could with a decision tree, okay? We don't need a ROC curve because it's 100%, okay? Their model accuracy, we tried to sort of reverse engineer the ROC curves, came to about 80%, okay? But again, they don't really tell you accuracy. They just say, oh, behavior behaves like this. You don't even know what the false alarm to positive rate is, really. And then the improvement of the best guess would obviously be a lot less than what we achieved. And their model capacity is also unknown because we don't know how many parameters they use. And all they could say is generalized. Hey, we generalized, which is true, probably because they tried on a test and validation set and got some good results, fine. But we know how much it generalized. That means we know that about 2 bits per bit, so the value of 2 correctly predicted results, if they were balanced, but they're not, so it's a lot more correctly predicted results per memory equivalent parameter is our generalization ratio. And then we get a confusion matrix, and obviously that's not interesting because the confusion matrix is perfect. And we can also check against the memory capacity of the decision tree. And as we do so, we find out we are absolutely not overfitting because again, 2.09 is about the information capacity of that decision tree. Any questions about that? So now we get to value proposition number 3. That's actually kind of the biggest highlight of this. Oh, there's a question. Have you tried applying neural network using your parameters methodology on that immunology case? Yes, we have. And the point is that it wasn't as good. And the reason it wasn't as good is because when we use neural networks, we use stochastic gradient descent. But our decision tree is actually deterministic. So we don't have to do a Monte Carlo method to train that network. It's preferable to have a decision tree if you can, right? Because then you actually can predict what's going to happen. Now, I believe that if you use a neural network and you train it a lot longer, spend a lot more time than 5.22 seconds, you can also get to high accuracy, and you may probably get to a little higher generalization as well. But hey, we got 100% and we have generalization. So it's kind of pointless. Does it make sense? Right. So, okay, more questions. Awesome. For the 100% interval, what's the confidence interval? There's no need for confidence interval. It's the 100% result. But the confidence interval can be derived from the generalization ratio, okay? Because we know it's 2 to 1. So what we can say is for each sample, so what you take is you take the generalization ratio, and it's a bits per bit measure, right? So now that 2 to 1 tells you how many bits per bit in your input can be sort of changed. Basically, if you think about, you add random noise to this, right? To a sample, that you can actually add more random noise to each sample until the decision changes. And that is obviously about 2 bits per parameter in this case, which you could actually convert into decibel for maybe easier to understand measure. Yeah, so how does our method work in cases where labels are noisy? So when labels are noisy, first of all, it's supervised learning, right? You're training your kid on, well, dolphins are also fish, right? So the only way to get rid of noise is to either get rid of it, that means you do annotator agreement, or to really add a lot more data. And I'm giving you an example. So let's say it's not 2, 4, 6, 8, 10, but it would be 1.7, 4.2, 5.8, 7.6, 10.3. You see that this is now noisy, but the rule would still be +2, right? It's just if there's enough noise, then you probably need a lot more data. But that's the only way you can get rid of that. So the rule that there's no data than enough data to find the rule is still true. It's just you will need more data to find the rule. Okay. But also mislabeling is a problem. There's nothing you can do in general. So incredibly fast method for identifying the biosignal is the value proposition 3. So here's what's interesting. If you have sort of cancer genomics, right? The typical problem is that you have a whole human genome, right? 21,000 genes. The 21,000 genes basically is a lot of attributes. And then let's say if you have only 500 patients or something, which is already a lot for a clinical trial, usually machine learners suck. They basically don't know what to do, because they're basically with 20,000 attributes, it's much easier to just memorize everything. So there's a bunch of techniques that people use, but if you think about it systematically, there's a big problem. The big problem is if you really want to sort of pick which genes are the ones that make the difference, because we know most genes don't, right? Most attributes of a data probably don't make a difference. So what happens there is what you want to do is you want to basically find out, okay, maybe we can find the 2-3 differentiating genes between the cancer cell and the non-cancer cell. It's called cancer genomics. So what other machine learners do is they just try, see if we include or exclude. And you see easily that this inclusion exclusion means, you know, you put a 1 or a 0 on each attribute for include exclude. And now how many 1s and 0 combinations can you put? Well, guess what? It's like memory, 2 to the power of n, the number of attributes. Now again, for 20,000 attributes, 2 to the power of 20,000 is a huge, huge number that you cannot solve. But with our learnability measure, you can actually, because our learnability measures that I just introduced obey the triangle inequality, we can reduce that to n squared. And with n squared, finding those numbers, you have a really interesting chance of finding this. So we actually worked with Cedars-Sinai on this, and then other hospitals as well on giving us cancer data. And it turns out they gave us a data with 584 patients, 21,000 gene protein expressions, and a 3-class problem: malignant versus non-malignant versus no cancer. And we find within minutes that VWA7 gene that actually has been found in the community before, but it's just for us to verify, and predicts ovarian cancer with 100% accuracy. And all you need is a 2-neuron predictor. And that's very, very powerful. That's basically finding that genomic signal like on the spot. And we work with a lot more companies now, sort of in the multi-omics realm to find that out. There's another question. No, there's no other question. Okay. So that's basically a very, 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 very powerful part of our tool. And that also helps to create features, right? So often we really don't know, should we include this? Should we not include this? With Brainome, we tell you, include everything and we'll figure out what we need, right? And that's a very powerful part of what we do. So now, all of this time you had to endure my talk, what I want you to do is, why don't you try it out, okay? So we have brainome.ai. If you just go to brainome.ai, we have a big demo button. You just click on the demo button, and I'll show you what the demo button leads you to. So you can take your own CSV file, your data, or you can just probably work with a preloaded data set just to quickly find out what happens. So I'll show you what happens here. So this is a preloaded data set. And the preloaded data set, actually, I don't actually know which data set we preloaded, but in this case, it doesn't even matter what it is. This preloaded data set has 202 instances, 5 attributes, 8 classes, and the best guess is 51.98% because it's pretty balanced. And now what you see here is, first of all, the class balance on the left. And because 8 classes, you see that actually it's not balanced, sorry, it's actually pretty unbalanced. So the majority class is 51 or 52%, and then the other classes are a lot less balanced here. So you see that here, class balance. Then you see our learnability. So we will count the number of parameters for decision tree and for neural network, and then obviously also deduce the expected generalization. These are basically identical graphs, except that lower is better for parameters, and of course, higher generalization is better for generalization. And then we give you that capacity progression that I mentioned earlier, where we basically ask ourselves, as we add more data, can we apply the same rule to less than when we had less data? And here's a real question. So in essence, your method chooses the best kind of learner for the task and replaces the hyperparameter tuning with this measurement-based science. Yes, it does. It's a lot more too, but of course, I just wanted to try this out. It's a lot more systematic approach. We actually don't choose models, we build them. There's no reason to choose models from a large set of things once you've understood how to build them and based on measurements. So we will tailor a neural network or a decision tree to your problem, rather than you taking something off the shelf and trying if it works, right? And so then also we have overfit risk, right? So we can actually give you overfit risk, which is basically saying, okay, without training, let's give ourselves a chance that the number of parameters that we know here actually lead to something that's general or not. And actually, in general, overfit risk for neural networks is always a little higher. And the reason for that is that, let's say you have something like 3 neurons, but 3 neurons don't do it, you need to add another one. Then you add a neuron that has to have all these parameters for all the inputs, and then you have to have another connection to your output neuron, and that's just for a 3-layer network. And so in a decision tree, you can just add a single branch, but in a neural network, you need to add a whole neuron. And that, of course, gives you a lot higher risk to overfitting because you add a lot more parameters at once each time you add something. But sometimes that's not true. Sometimes it's the other way around. And then also, in this particular one, we have the problem that there's a sparse class here. You know, this class that's just on the right to the blue thing is very sparse. So we will give you recommendations. And one of the recommendations is here, actually, sparse class with 2 instances will result in overfitting. That doesn't result in overfitting the entire thing. It results in overfitting that sparse class. So maybe we can predict we have a general rule for the 51%, but we may not get a general rule for this sparse class, right? And that may be fine or may not be fine. Because as we know, all rules have exceptions. Maybe that super sparse class is just the exceptions to the general rule, right? So that's something why it's a recommendation that you have to look at afterwards once you get there. But there may be enough data to generalize is a very good one, because that usually means we should do something. And it is true because the capacity progression looks like we are very almost converging here. From 40 to 80 is a very small jump, and from 80 to 100 is 0 jump. So if we now do it, we say build, and then Brainome builds a model based on the measurements, and will give you obviously the output as in accuracy and in model efficiency, generalization ratio, model capacity, but also basically as a confusion matrix. So you see basically everything that happened here. And of course, that will be the thing to look at to find out whether we overfit on this sparse class, right? So that's what it is in general. So the next thing is what you don't see here is below the predict, you can actually download a Python predictor and then use it on your data or on your test data or your whatever, or edit it and say, okay, but I want this slightly different, and basically go from there and build stuff. But I completely want to invite you to try this out on www.brainome.ai. There's a lot more information too, a lot of the scientific papers, some introduction videos, some really detailed explanation of the measurements, and also obviously that demo that you can just try. And by the way, the demo is obviously restricted to very small data sets because we pay for that cloud time, to be frank. But you can also get a free account. And so if you sign up, then with a free account, you can start doing real work with your own data set. So I really encourage you to sign up there and just try your own data set and don't believe me, just try it out, really. Just you know, play around with it. It's also a lot of fun, and I guarantee you will learn a lot too. And especially for you guys who stayed all this long, it's gonna be very interesting. Yeah, that basically concludes my talk, but I intentionally didn't want to talk the full time. I really wanted to open to questions because I feel like there's going to be a bunch of questions.
Thank you, Dr. Freeland. It's very tempting propaganda to BrainOhm, and it's definitely bringing a new angle of looking at the metrics of a machine learning, but we are way out of time. But I do want to ask a question, which was also very interesting from my point of view, that what are the limitations of your method and BrainOhm? Seems like it's perfect so far.
It's very important that the limitations of our methods are, we only do classification. So we don't do regression, and we also don't do unsupervised learning. And another limitation is that you have to have constant dimensionality problems, right? So if you have like random peptide sequences that are all different lengths, that's going to be very difficult. This is the limitation.
Technical, yeah, that's understandable. But if anyone else have questions, feel free to type it in the chat, but we'll have to stop record and stop this Zoom meeting. And I'll have to forward those questions to Dr. Freeland, and we can answer through emails and exchange through emails, etc. Yeah, all right,
There's one more question.
Okay, one more.
Okay, specific to decision trees, how does your method change the training process? Not sure I understand the question. So we have, what we have is we call equilibrium energy decision tree, which is slightly different from standard attribute-based decision tree, which makes it easier to measure. But other than that, it's a decision tree. And yes, you're right. You can build up a decision tree incrementally. And that's why it's one thing we do as a baseline before we use neural networks. Does it make sense? Training is not changed, no.
Okay.
Yeah, our system, quick question. Yeah, our system does automatically do cross-validation, completely automatic. And it's very important that the way we do it is the following. We will split your training, the data set that you give it, into training and validation set. And that's very important because we do so because we want the same complexity in the training and in the validation. So it doesn't make any sense to give it a validation set that has lower complexity, because then it would be easy. And it also doesn't make any sense to split up a validation set that has higher complexity. This is usually solved by cross-validation by splitting up 10-fold or something, 10 folds. But that's just a sample. 10 folds are just 10 samples. It's much better to measure the complexity, because to go back to the human analog, when you train some kids on some math stuff, you want to actually test them also on the same task rather than on a more difficult or on an easier task, right? The system automatically detects if the sample size is too small and will tell you, yes.
That should be all the questions.
I think that should be on it. Okay, thank you so much. Thank
you,
everybody, for listening.
Dr. Freeland. Yeah, thank you so much for talking today. This is a very informative talk. All right, we'll see you all next month, Friday. Thank you all.
Okay, thank you.
Bye.
Oh, there's one more. Thanks. Okay.